Swayam Prabha. Digital India. Educated India.
Unfortunately, none of the models will explicitly come and say, hey, I am a delay model or something. It will be general description and you just model it. It just so happens that it will be some form of delay or the other which you can recognize. If it explicitly says delay, good for you. If not, still there will be delay existing. Especially this example. The chemical company makes chemical called no bug used in pesticides. They dump the byproducts in the say river once a week in batches such that the concentration is about 420 parts per million. So, we can assume that the river has 1 million gallons of water, that means 420 gallons of no bug are dumped per week into the river. During the course of the week, the chemicals are absorbed by the river's natural cleanup process. The average absorption rate is 2 days. Model the above system. Go ahead, how will you model this? The model will be quite simple, but description will be quite elaborate. Since I just covered first order material delay, logic suggests that it should be similar to that. Hopefully, you have got the model, this one, or at least you are thinking of a model like this, not yet drawn it. So, it's very simple. Again, when I teach, I may use words like inflows and outflows and stuff, but you can use some proper rates like dump rate, which it represents what is actually happening. Absorption rate is what they have told. Absorber cleans reverse natural cleanup process. So, it will clean up whatever is in the stock, it will clean up with an average absorption time. So, I will just write the equations in red. So, here the average absorption time is given as 2 days, right. So, ensure your time unit in the model, in your model time unit is selected as days, ensure that. So, absorption rate is nothing but no bug in river divided by absorption time, because it is a rate, stock over time it has to be. So, no bug in river divided by absorption time is what you write here. Initial value you can put it as 0 in stock, so initial value is 0. So, now to kind of simulate, let us take a very simple case. Let us start with a dump rate as just a pulse quantity. We already seen pulse before. So, pulse has 2 inputs, one is the start time, other is the duration. So, at time 0 there is one pulse 1 unit occurs at time 1, but what we already know it dumps 420 gallons, right. So, I just multiply this by 420. So, dump rate is 420 multiplied by pulse 0 1. So, you can make this in Vensim. So, you have all the information you need. The units of dump rate will be gallons per day, no bug units is gallons, there is amount of no bug in the river, gallons. Absorption rate again gallons per day comes from here, gallons comes from here. Weekly dumping is happening, but we will just take it as only one beginning of this week it happens. So, let us just observe that, then we will model the next part. Okay. This is how the model looks. NAT, natural absorption time, I just came up with some acronym, looks like it. If you look at the absorption rate is no bug by NAT, NAT is given as 2, this is easy one. dump rate is 420 into pulse of 0, 1, just a pulse input. So, if we run the model, we can see that Nobug increases and then has exponential decay. So, the halving time would be about 70% of your average delay. So, 0.7 into D is 2, so 0.7 times 2 is about 1.4, 1.5, about a week, a day and a half time it will come into half the quantity. Okay, right. Any questions on this so far? Right. Now, what do you think will happen if we dump every week? It will go up, it will come, and again it will go up, come down, go up, come down. Is that what we expect? Let us see what happens. So, dump rate oops, what did I do? Yeah, let me get that guy here. There is another function called as pulse train. What pulse train does is, as the name suggests, it gives a pulse input periodically. So, in this case it gives a pulse input starting at time 0 of a duration of 1, and that repeats every 7 days, that is once a week. Every 7 days it repeats, and the end time is 50. After 50 time units passed, no more dumping happens, that is after. Okay. So, that is a very simple model that we have. So, it is called pulse train, you can look it up in the help file. So, every week 420 gallons is dumped. Okay. So, let us observe what happens. I am going to run the model. So, we go to Nobug, let me do a causes strip. It nicely occurs, as we see here. The top graph is the stock increases up to 400 on the day of dumping, 420, and then gradually comes down. Absorption rate also happens, and so nicely fits our model right here. And dumping happens only once a week, which is verified by the bottom graph, which shows there is a dumping happening every week. Now is the actual fun part with SD, where we have to do sensitivity analysis. Just making this is okay, but then to get insight, we can find out, say for example, what happens if the natural absorption time instead of 2 days become 4 days, because of various reasons. It has lake's capacity to absorb has reduced, and now the natural absorption time is 4 days. So, let me just make it 2 to 4. In that case, what do we expect to happen? Can we have the same behavior? Behavior has to be the same, right? Once it dumps, it start absorbing, correct. But then let us see what happens. Let us simulate. Nobug. I just made the absorption time 4 from 2 days. The dumping is the same, absorption also happens, but now you see steadily the peak from 420 has moved closer to 500, right, and 480 is the peak, and it does not go now below say 90. There is always some Nobug in the air, in the river constantly. So, as absorption time increases, say logically speaking, now if the absorption time becomes average becomes say 7 days itself, then by 7 days we can expect roughly little more than half of the Nobug would have been absorbed. So, it will start accumulating. So, the accumulation effects is captured in this stock right here. So, if we did not have the stock, we may assume that as soon as a dump, eventually it will get absorbed, but it is not going to get absorbed until I stop the inflows again, and then allow it for some time to slowly absorb and decay completely. That is an interesting one. Average absorption is 4 days or 12 days, of course it is going to keep increasing. Instead of we have tried with 4 days, you can try with 12 days. The next is interesting. Instead of dumping 420 every 7 days, what if we do 60 every day? we expect some behavior or different behavior. The quantity is the same, they got permission with government to dump 420 gallons a week. What difference does it make if I do it every day or do it once a week? Let us see what happens. So, I am going to go back and take the natural absorption time back to 2. In 2 case it came up and then went down very consistently, nice graph I got. Now, I go to the equation of dump rate. And we are doing 60 gallons a week every day, time step is day. So, I just write 60, it means every day it will be 60. So, let me simulate. See, the absorption time is for whatever quantity I put, it takes an average of 2 days to deplete, correct. So, now if I dump every day, it does not give enough time for the river to absorb everything. So, eventually the total amount of say no-bug in the river actually increases to, what is it, about 120 looks like, right. That is a interesting thing, but if you think about it logically, what we did is when we dumped it once a week, we gave time for the river to recover. In this case, we are dumping 60 every day. So, by the time it starts processing 60, the next 60 is coming in every day, it takes time, river cannot process so much, but still so there is some amount of about 120 gallons that is end up in the river, even though nothing else changed, right. Just the simple act of the same quantity but different times actually has a nice kind of so it is better when there is a time given for river to recover rather than when it is very less, though the quantity is the same. So, these kind of insights you can get only if you play with it, simulate it, try with different values, and this is a kind of policy which is just a simple model can use to explain different policies. People want to the same example, do you allow them dump once a week or dump every day, though the quantity is the same, we can find that actually analytically there is difference in behavior and it does not kind of not a very complicated model to explain that. Second order delay you can imagine as cascading two first order delays, that is it, that is called a second order delay. So, the tank example looks very similar. So, the stock flow also we may able to guess based on this. So, what we are going to do is when you do a second order delay, we will assume the total delay time is divided evenly among both the levels. So, if you want to model the second order delay, we just take up inflow stock 1, let us call it exit 1, stock 2, this is your final outflow. This is affected by d by 2 and this is affected by d by 2. If you want to model it Vensim directly as a function, we will do it as inflow stock outflow t. Here we will write the equations for outflow as delay n as your in d initial value if any, then we will write the order as 2. So, this is your order. Here the equations for exit is nothing but S1 by d by 2. So, the equation for exit is S1 divided by d by 2. So, exit is S1 by d by 2, outflow is S2 by d by 2. Okay. So, this is second order delay. Do a third order delay, that is nothing but your inflow stock 1, let us call it exit 1, then I have stock 2, then I have stock 3, outflow. So, when I say first order delay, there is 1 stock, second order delay 2 stocks, third order delay I am looking at 3 stocks. Once the material is conserved, so all the stocks and flows are getting interconnected, and now the delay time is evenly divided among 3 of it. So, the equation for exit 1 is S1 by D by 3, exit 2 is S2 by D by 3, and outflow is S3 by D by 3. So, evenly divided. So, the average delay time continues to be D. Here as soon as outflow happens, D by 3 amount starts flowing out of exit 1 as soon as inflow happens, and after D by 3 1/3 of the time, this stock will start to peak, and then of 2/3 of the time this stock will start to peak. So, that is the peak of the outflow. When this one peaks is when this peak outflow will occur. To model it in Vensim, again we can use the similar delay n function with a third order delay. So, this third order delay I just showed you, delay is divided evenly among 3 levels. Suppose delay D is distributed evenly among n stages, then instantaneous outflow of stock I will affect the subsequent stock. The delay is evenly divided among n stocks. So, for each level I have D by n. So, we have 5th order, 6th order delay.